Logarithms are, I'll put this back over here again. Logarithms are part of this. A logarithm is actually the thing that connects them and makes them, when you think about it at a very theoretical stance, exponents and logarithms are the same thing. It's just two different ways of writing it. If I had a equals b to the c, where a, b, and c are numbers, or variables, doesn't really matter, I can also write that as log base b of a equals c. Most of us in our math history see this and have seen this, and we've done exponents, and then we do roots. Roots are also linked to these things. Exponents and roots are inverse operations, but both of these can be written as either type of function, either as an exponential function or as a logarithmic function. But they are one and the same. We did an introduction to logs before, probably last class period, I believe. So now we're going to talk about specifically common logarithms, or that's what this one is called. It is called the common logarithm. It is the one that gets used the most if you look at your calculators and your phones, and it has a log button. If you just talk about and just write log like this, it is understood and assumed that the base right here that's not written is 10. It's kind of like when you first learned about x's. And we did variables back in the day. And you're like, well, how many x's is this? It's 1. Well, why don't we write a 1? Because it's understood that the 1 is there. When we just write log, it is understood that the 10 is there. And what is this saying if I were to convert this into something, into another equation? If I had log of x, and I typically will put parentheses here. I would encourage you to do the same thing so that you can see that it's function. But if I have the log of x equals y, if I had to convert this out of logarithm back into exponent, which you need to be comfortable doing and confident in doing, I say not a bad idea, even though we know it's implied that it's a 10, to go ahead and just write the 10. When I do that, I'm saying 10 to the this power is equal to that. The mistake people make is they go, well, it's 10 to the x equals y, and that's not how a logarithm is structured. This would be rewritten as 10 to the y power equals x, or 10 to some power is equal to x. So the common log, again, common log is base 10. So when we get to something like this, problems would say simplify this. I was like, oh, this is base 10. So I'm really asking myself as I look at this, 10 to what power is 10? Or when you are uncomfortable at the beginning stages, you're going to look at your calculator, and if you go to your calculator and verify this with me right now, you certainly can. Probably not a bad idea just so you know where the logarithms are. So let's do that now. So when you use your calculator, 10 to what power is 10? The answer was 1. And if we do this one, so I'm thinking 10 to some power is equal to 0.01. 0.01, we're working in base 10 systems. Some of you remember this, right? This is the 10th digit. This is the 100th digit. So I could rewrite this as 10 to some power is 1/100th. Well, 100 is a base 10 number. So 10 to the x is equal to 1 over 10 squared. So how do I go from 10 to an x power to 10 to this power? Well, my x would now have to be in the denominator. And whenever you flip sides of the denominator, this on the right side would be 10 to the negative 2 is equal to 10 to the x. So my x would be -2. And if you plug it into your calculator, it would give you the answer of -2. All right. And then the third one, 10 to what power is 1,000? Well, it's 3 zeros. So that'd be 10 to the, it's not 10 though. It's just the number 3. So when you're doing negative exponents, that is, I'm ending up with a value less than what it is. So 10 is going to turn into something smaller than 10. I'm going to have a, see there? 10 is growing. I'll have a value bigger than this. All right. Once I go past, if this number in here was like 2, 10 to what power is 2? This value here would be a positive fraction because we've taken some type of a root of 10, like the 3rd root of 10 or the 10th root of 10 or something like that. But once I get less than, yeah, down like this, now I'm talking about negative exponents. Anyways, I'm getting ahead of myself. The other most common type of logarithm, although it's not called the common log, it's called the natural log. All right, you got this guy, Euler. That's how he pronounces his name. Euler is a mathematician. Euler came up with a lot of amazing things. Probably the one thing that he gets, I think, undervalued for is what's called the letter E. But it's actually a number. You've seen this number before. Pi is the ratio, if I could infinitely measure the ratio of the circumference to the diameter of a circle. If I could, again, measure that infinitely, 3.1415926, and it goes beyond, goes beyond, goes beyond. Pi is a never repeating, never ending decimal. It's referred to as a transcendental number. The other transcendental number is E. Again, if you go to your calculator, if you're on your phone, you turn it sideways, but otherwise it might be behind, and by behind I mean if you have a natural log button, an ln button on your calculator, if you go second that button, it might show as then E. If you have a cell phone, you actually see e to the x. So if I do e to the x, I just hit that number. Hit e to the x, it says 1. But if I go 1 e to the x, it tells me the value. If you press the number 1, then you press the e to the x button. It tells you the e is 2.71828182884. And it keeps going on and on and on and on. So E is a number. And it's actually such a significant number, it gets its own special logarithm called the natural log. So the natural log is log base E, but we usually don't write it as log base E, we write it as ln. People say, well, why isn't NL for natural log? Long story, but we won't get into it, but it's ln. So on your calculator, if you look and you see ln, which you will on your phones or on your other calculator, what ln means is that means natural log of x, or it's going to be log base E of x. And we'll see a little bit later today where E gets, shows up, becomes part of what we're doing in our curriculum, emerges, if you will. It's discovered that that's really common in certain areas. All right, so that's what the natural log is. And without going into a long history of Euler and the great contributions, just remember E is Euler's constant. All right, there's E. So that means if you take your calculator, if you have a cell phone type calculator, you hit the number 8, then you hit the ln button. If you have a regular calculator, you probably hit the ln button, it says ln parentheses, and you type the number 8 and hit enter. It gives you this value. So what does that mean? Again, if we go to translating back and forth between exponents and logarithms, that means natural log of 8 is the same as saying log base E of 8, since that equals 2.07944154, etc., that means if I convert it into exponent, that means e to the 2.07944154 minus some rounding errors. So if I take that number, take that to the, take e to that power, sorry. E 2.07944154 e to the x, my calculator gives me 7.999999998. Basically, that's the value of 8. So when you're taking the natural log of some number, just remembering, what does that mean? It means that if I took e to this power, it will give me 8. E to that power gives me 8. E is my base. This value here is my exponent, and then that's what it results in. And I have another missing slide. All right, so that's what I was apparently missing on my slides. Like we did with the base 10 numbers, we look and say, okay, what is going on here? And at the beginning stage, not a bad idea just to say, well, this is the same as saying log base e of e to the third. And I'm saying e to what power is e to the third? The number would be 3. Because again, if I'm converting back and forth between exponential and logarithmic form. So e to the third power is e to the third power. It's a little bit harder to do these and set them up than like the 10, that made sense. Like, 0.01, that's 1/100th, that's 1 over 10 squared, that's 10 to the negative 2. Here, it's e isn't an easy number. I mean, by its very nature, it doesn't work well that way. So on the right side, we're going to have log base e of the 8th root of e. Here it's trying to get you to remember, what is this as an exponent? If you can remember this as an exponent, life becomes a lot easier, because then I'll have log base e of e to the 1/8 power. Roots are fractional powers. Square root is some number to the 1/2 power. And again, if it's cubed, that's an exponent. If it's 1/3, that's a root. One is multiplying it by 3. One is saying, well, what number times itself 3 times? Gets you there. So then the answer would be 1/8, or e to what power is e to the 1/8. So now we're going to solve. Now we get to doing some algebra with this. Easiest thing to do is take it and convert it into exponential form. Most people don't think in logarithm base. If you work in it enough, you can get the hang of it, but right now, not as much. But I'm going to convert this. So my base number is e, my exponent is what it equals, and then what's inside the log. All right, so again, this is all that it is. We started out doing this a few slides ago, converting back and forth between exponential and logarithmic to exponential. Sometimes it helps, because right now this helps. The reason why I know it helps is this is just a number, e to the 5th power. So we go to our calculators, verify it with me so that you know how to operate your calculator, whether you have it as, so if you're using cell phones, you would hit the number 5 and then you hit e to the x button. If you have a regular calculator, you're looking for the e to the x button, which might be second natural log, or maybe you have an actual e to the x button, and then you would type in the 5. But either way, it's 2.7, the whole thing of e to the 5th power, and I get 148.413616. There we go. People ask, how much should I round? My recommendation is don't. If it's 4, 5, 6 decimals, put them on there. The minute you start to round, especially early, you lose specificity. All right, so e to the fifth is that number, and that equals 3x, and then you go, oh, well, now it's just, again, back to algebra. Divide by 3, divide by 3. X equals 49.47105, so we'll just go, yeah, we'll just leave it like that. And if I wanted to check that, I could take that number, multiply it by 3, and then take the natural log of it, and it should give me something, again, it will be rounded, probably 4.999999, something like that. It will get you really close to 5, but not exactly at 5. And the reason why is we're doing natural logs now. It's not quite as simple and easy. So here's where one thing shows up. Compounding interest type formulas. There's when you have different types of investments can be, a lot of times you're going to get either a quarterly or a monthly interest rate. Right? You get a home loan, here's what's going on, and it's calculated monthly. So that means once every 12 times a year is running through things. You can actually get to more specific, and you can actually do ones that are daily. And then if you get to this is what would be considered continuous. What you're going to see on the short term for an investment in difference is not going to be much, but in the long term becomes a much more significant value if you find anything that does continuous. It's not a very common thing in the realm of what you might be investing in or in what type of loans you might get. But in a case like this, there's that formula. A equals P times E to the RT. And it tells you right here in the problem that A stands for the amount that I end up with. So this says here, A is 2509.30 equals. P is the amount of the loan, $1,600. I don't have to have necessarily the dollar value there. All right. My rate is 9%. So I'm going to have E raised to the 0.09 for a duration of 5 years. So that'd be times 5. So what we're going to just do here quickly is just verify that these numbers do work in this formula so that you know that you're operating your calculator successfully. And as you're going through and you're thinking through all of your order of operations, P, E, R, M, D, A, S. Why do I keep writing it? Because lots of mistakes on the first couple exams related to these orders. All right. So I have exponents. I got to deal with the exponents first. And actually within exponents, there are parentheses. Because within the exponents, there is multiplying going on. So that has to happen first. So I'm going to have 2509.30 equals 1,600 times E to the 0.09 times 5, which would be 0.45. All right. Then order of operations. Now I'm going to do my exponents. I'm going to have E to that power. So again, this would be a good idea to be verifying that you're getting these same numbers in your calculator that I am in mine. E to the 0.45 power is 1.568312. And then I'm going to take that number and then times 1,600. And I get 2509.2995, which we had over here as rounded to 0.30. Where this is going to come into play now is we'll have a scenario like this, and one of those little nuggets will be missing. Either the final amount is missing, what was the principal amount to start with everything else given, what was the rate, or possibly how much time does it take. So I thought I had a problem in here that did that, and I don't. We're probably coming back to it later. All right. Properties of exponents. Let's do a quick review. A to the x times a to the y times a to the z. If I have three things all with the same base and I multiply them together, this is the same as a to the x plus y plus z. Same bases and multiply, we add exponents. B to the x over b to the y is equal to b to the x minus y. And then the last thing we had was like c to the x to the y power. So if I have something to a power raised to a higher power, powers raised to powers, that's when they multiply, x times y. We're doing this because logarithms and exponents, they're just the same thing written a different way, which means we are going to have properties of logarithms. If I have log base b of x plus log base b of y, that will be equal to log base b of x times y. More times than not, we're actually going to use that property in the other direction. We're going to be given the thing on the right. We're going to have a couple things multiplied, and maybe one of them is a variable. I can then split them up, and again, trying to get my variables by themselves and then solve for variables. That'll be some of the process that we're going to go through. If I have log base b of x minus log base b of y, can you guess what's going to happen? I'm subtracting, much like exponents, which means I'm going to have division. So it's going to be log base b of x over y. So if I have a complex fraction, something in a numerator denominator, I can actually split it up into two things that are no longer fractions as a logarithm. All right. And then the fun one here, log base b of x to the y power is equal to, whatever the exponent is, it actually will travel out in front. It becomes y times log base b of x. This becomes a very, and will be a very useful tool, I'll say it a third time, very useful tool when my variable is in the exponent. All right. And then one more property, and that's the change of base. Because our calculator only has base 10 and only has base e for the natural log, well, what happens if it is log base 7 of 4? 7 to what power is 4? I don't know. That's really hard to do. It can be rewritten as log of 4 over log of 7. And now, because I didn't say what the base is, it's implied that it's base 10. I can convert from a weird log base to this. Be careful, though. This is not log of 4 over 7. All right, so remembering which way it goes for dividing. If I have two logs that are subtracting, I can combine them into dividing inside. But here, I'm doing two separate logarithms of two different numbers. I'm not doing the log of two numbers inside of one log. And that was the next slide that I had. Well, I just did it the other way around. Thinking ahead of myself. So now we're going to use this to solve. I have, now, a couple ways I could go. I'm going to do it two different ways. So I'll do it over here one way. I'll do it down here a second way. The first way I'm going to do is I'm going to split this up as natural log of 3 plus the natural log of x. The reason why I did that is because the rules of logarithms are when I multiply, I can split them apart and do addition. So now I've got my x all by itself, and this equals 0.18. And then I'm going to, just like I did back in the day with algebra, I'm going to subtract things that are not natural log of 3, subtract natural log of 3 from both sides. I'll have then natural log of x is equal to 0.18 minus the natural log of 3. And the natural log of 3 is a number. At any point in time, you can just plug it in your calculator, do it there, and then go 0.18 minus that number. But now I have natural log of x equals some number, which is really log base e of x equals that number. Which is really saying e to that power, 0.18 minus natural log of 3, that's just one giant number, is equal to x. So that's one way I could do this problem, using the properties of logarithms. Another way to do the problem up here is if I had the log base e of 3x is equal to 0.18. So I just took that original problem again, wrote it as log base e, and then recognized that that means e to the 0.18 power is equal to 3x. Just switching it back and forth from log base to exponential base. E to that number is a number. Solving for x, divide by 3, divide by 3. So x will equal, as you plug it into your calculator, do 0.18 to the e power, or sorry, e to the 0.18 power. Verify this in my calculator. Also, again, like I said, good habit for you to do it too, to make sure you know how to run it. If you're not getting the same answer, this is talk to someone or myself to see what you're doing. I get an answer of x equals 0.39907. Yeah, so if I have the same log base of two different things, and they're both equal to each other, then the things I'm taking the logs of also had to have been equal to each other. What normally throws people off is they see the base A, like, oh, what does that mean, something different? No, it just means base A, because it doesn't really matter. If I have log of x equals log of y, that meant that x equals y. But it also means if I have something like this, if I have x equals y to the t, and I want to find t, like time in one of those other equations, if I take the log of both sides, if I take log of x, it would equal the log of y to the t power. And then, using properties of logarithms, log of x would equal t times log of y. Well, now that's how I'm going to get my variable out of the exponent. So that's why it's important to see this. Like, hey, if I have two things that are equal, if I take the log of both things, still equal, allows me then to bring my exponent down in front. So now we're going to do a little bit more. Let's combine. Let's see if we can work on this. So now I have log base of the same thing. They're both base 10. Log base 10 of this, log base 10 of this. I'm subtracting. Properties of logarithms would tell me that that is equal to log of x plus 2 over x equals 2. And then I get it to a single logarithm, and there's nothing here that jumps out. It's like I don't have something that's base anything going on. I've got a whole bunch of variables inside. So what I want to do is now try to convert that, remembering that this just log is also, that's base 10, convert it into exponential form. It's going to be 10. 10 is the base of my logarithm, which means it's the base of my exponent. The exponent is what the whole thing equals. Equals what's inside, x plus 2 over x. $100 is equal to x plus 2 over x. I don't like working with fractions, so I'm going to try to get rid of the fraction. Or, we could go back to some pre-algebra days. If I take that, make it a fraction. Do you remember doing this? Cross multiply. 100x, because that's 100 times x, equals x plus 1, 1 times x plus 2, which is just x plus 2. So either way, what I was going to do is I was going to multiply this side by x, and I was going to multiply this side by x, so that way the x's reduce. I'm still left with the same thing over here on the right. Subtract x from both sides. Not a real easy thing to do when you're looking at that original equation and say, yeah, I might be able to guess and check my way to it. No, you won't. But in this process, just trying to get us in the habit of using our properties of logarithms, combine it into just one single algebraic statement, then using conversion between logarithms and exponents to get myself moved out and into something usable, like this. We're going to do the same thing here. I'm going to pause and let you give a try at some of this using properties of logarithms. It's very similar to the last one we just did. It's adding instead of subtracting in the middle, so it's going to be slightly different. And see if you can at least start getting this set up. So for those of you watching online, hit pause, work on it. For everybody else in class, I'm going to hit pause and you're going to work for a little bit. So getting started with this one, since I have x's that are in two different logs, I want to try to combine those so I have all my x's together in one place. So I'm thinking, is there a way that I can combine this logarithm with this logarithm? Well, they're the same base. Same bases that are adding means that I will multiply. So log base 2 of x times x minus 1. So those two can combine together into a single expression. And this over here equals 1. I can simplify that some more. X base 2 of x squared minus x is equal to 1. Now I have my entire algebraic expression in one place. And then I can look to see about how to get this out of logarithmic and into exponential form. So my base is 2, because that's the 2 right there. That's the 2. The exponent is what the whole thing equals. So it's 2 to the 1 power equals x squared minus x. Or in other words, it's 2 equals x squared minus x. I need to find x. I need to solve for x. I have a quadratic. I know it's a quadratic because it's an x squared. Process for solving a quadratic, set it equal to 0. Look for a GCF. Doesn't exist. See if there's a way to factor. Do I know two numbers that multiply to 2? Negative 2, so it's a positive and a negative. They multiply to 2 and add to negative 1. Well, look at that, I do. Because negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. That's my middle term. So then x plus 1 equals 0. X equals negative 1. X minus 2 equals 0. X equals 2. So if I were to go back and do this in original logarithms, well, it's going to be base 2, so it's going to be harder. But let's say I put the 2 in there. Log base 2 of 2. 2 to what power is 2? 1. So this is 1. 2 to what power is... We'll go ahead and do that just for... I'm just going to take this one. Log base 2 of x minus 1. I'm going to put this number into it for x. So this will be log base 2 of 2 minus 1, which is log base 2 of 1. So I'm really saying 2 to what power up here? It's supposed to be a question mark. 2 to what power is 1? Anything to the 0 power is 1. So if I would have taken this number 2, put it back in here, this would simplify to 0. This would simplify to 1, and 1 plus 0 is 1. So now we're going to go back to this investment strategy formula, but we're not going to use E this time. So E is only this very unique scenario where you're doing it and you have interest that gets compounded continuously. Very rare. So and this is the more generalized formula for when it gets compounded a different way. So in this way, we are going to be compounding, what does it say? Quarterly. That means N is 4 in that formula. R is still the rate. 5%, but I need to write it as a decimal because all the other numbers are decimal numbers. I have an initial investment of $2,000. That's my principal. And it asks, how long does it take an investment of $2,000 to double? So that means my ending amount will be $4,000. That's my desired amount. Now, let's take our values, plug some of it into that equation, and see what I can come up with. 4,000 equals 2,000 times 1 plus R is 0.05, N is 4, raised to the 4t. I don't know what time because the question asks how long does it take. So that's what it's asking. How long? How many years is this going to take to happen? I have an algebraic equation. I'm going to start to solve as best I can this equation. My t is way up here. I need to eliminate anything that's far away from it, so I need to eliminate the 2,000. It's 2,000 times, so if I take both sides and divide by 2,000, it will then be 1 plus, and why don't we go ahead and just convert this into one decimal place, one decimal number. So if I take 0.05, divide that by 4, that's 0.0125. Do plus 1, because that's what's inside. So this will be 1.0125. So I've simplified just what's inside the parenthesis there. Raised to the 4t. I have my variable in an exponent. So this is where I'm going to use logarithms to get that variable out of the exponent. I'm going to take the log of both sides because that was that one property we saw. The log base of the same base, if they were equal, I can take the logs of both sides, they're still equal. Log base 2 is a number that I'm just going to leave right now as log base 2, so I don't have to write out a whole bunch of decimals right now. Equals. I have a log of something raised to a power. Powers raised to powers, they multiply in exponents. When I have powers of logarithms, it also multiplies, but this exponent gets to travel down to the front. Be 4t times the log of 1.0125. Which again, the log of this, although it looks like it might be variable-ish because there's letters and all, but this is a number. You plug in 1.0125, take the log of it, it's a number. I have 4, I have t, and they're all multiplying. And I need to get t all by itself. So on this side, I'm going to divide by 4. And I'm going to divide by the log of 1.0125. On this side, I'm going to do whatever I did to the other side, divide by 4, and the log of 1.0125. When I do that, 4 divided by 4 is 1. Log of this divided by log of that is 1. I am left with t. And then it's a matter of, can I type this into my calculator correctly? And here's now where I might actually do some decimals. The log of 2 is 0.3010. It's 02999, so I'll go 03. In the bottom, I'm going to take the log of the number first. So the 1.0125, if I take the log of that, it's 0.005395, et cetera, et cetera. Verify these numbers as you go along, but it's the 00539 times the 4 that's there in the denominator. My denominator is then 0.02158. And then if I divide 0.30103 divided by 0.02158, t equals 13.949, or just under 14 years to double. So if you are investing at a 5% interest rate compounded quarterly, you can expect your initial investment to double in about 14 years, just under. Not a great investment for doubling, but better than going with a low interest or just something that goes with inflation. Inflation is usually between 2.5% and 3.5%. All right. So now I will go back to this slide. Shrink that down so you can see it all in one spot. But now, same idea, but how long will it take if the interest rate is 5.5% instead of 5%? I'll hit pause, you do some work, we'll confirm answers in just a moment. What if the interest rate is 5.5? That's what I want you to work on here in the next couple of minutes. So working, getting this set up. Similar process, 4,000 equals 2,000. 1 plus 0.055, so 5.5%, 0.055 divided by 4, to the 4t. This is 1.01375 to the 4t is equal to 2. I divided that 2,000 across, same as what I did before. Exponent is where my variable is. To eliminate it, I'm going to take the log of both sides. So I'll have log of 2 equals log of 1.01375 to the 4t which is the same as log of 2 equals 4t times the log of 1375. To solve for t, I divide what's not a t. So I have t equals the log of 2 divided by 4 times the log of 1.01375. And I believe it's about 12.6909, so 691. So you've been able to double your money and shave it off over a year by having a 0.5% difference. So in dealing with a lot of these, and a lot of what you're going to have is probably less about investing for your future, but more about when you buy your first house or have a car and you have to pay back things. You're not earning money, you're paying things back. And they argue, well, it's only a 0.5%. A 0.5% can be a big difference. It depends on, and we're only talking $2,000. You get a car loan and you're doing something in the $20,000, $30,000, $40,000 range. You're talking about a significant amount of money by having, quote unquote, only a 0.5% difference. Knowing the math, knowing how they calculate can allow you to get there. And first time you are home buyers, you'll actually get a document they're required by law to show you. Shows you the entire amortization process and shows you literally every month of an entire 30-year loan, if that's what you do, how much you're paying off in interest and how much you're paying off in principal, to realize that the first 15 years or so of your home loan, about 80% of what you're paying every month is just paying down interest. You're not actually paying off the principal to your house very much. It's a little depressing, but then the fact is, in 30 years you'll have a house and might actually own it outright.
Won't be yours for 30 years.
It won't be yours for 30 years. That's right.
Make sure you give
There we go.